This video will cover how to work ANOVAs using the 6 steps of hypothesis testing from the Nolan and Heinzen book, Statistics for the Behavioral Sciences, in Dr. B's statistics course. Alright, so just one example for you in this section. You can also watch the Exam 3 review to get another example. And this is kind of a silly one. You can tell it's from a textbook because it's Susan Sound. But we're going to predict that students are going to do differently on tests with different types of noises in the background. So this is sort of an attention study where we're looking at either constant background sound or unpredictable sounds, which evolutionarily should be more shocking and distract you, or no sound. So we're randomly taking 24 students and dividing them into 3 groups of 8. So that's random assignment. They're studying for 30 minutes. Boring. And then we've got our 3 groups. After they're done studying, we give them a multiple choice test. Okay, so here's the data. If you want to enter this into SPSS and try it. If you don't know how to work SPSS, I have a different video. You're going to watch the Using SPSS One-Way ANOVA with Compare Means. Okay, we'll match what we've done in class. There are 2 one-way ANOVA videos, so be sure you're watching the one that's Compare Means, otherwise you'll be confused. But remember, when you set this up, you need some sort of group column where you got your 1s, your 2s, etc. And then some sort of column for your scores where you have all of your DVs, 7, 4, 6, yada, yada, yada. Okay. And that way that each person gets their own row, and SPSS knows what the group designations are. Okay. So step 1 in the 6 steps of hypothesis testing is to check for assumptions. Okay. So is the DV scale? Okay, I could get none of these questions right, so it's actually a ratio scale, so yes. Second question is it random selection? Well, these are students, so I probably couldn't get every student ever, so probably not. That's a pretty unattainable goal. But can we randomly assign them instead? Oh yeah, they said they did that. Good, yay. Third assumption, is it normal? Well, I can't assume it's normal. If it's 30 people or more, I can kind of say yes, but I only have 24, so no. And then the last one, which is new, it's listed as homoscedasticity in your book. I've always learned it as homogeneity. Either one, equal variances. So how do I check for equal variances? Well, it's actually a test for it, but we're not going to do that. We're going to do it easily. We're going to take the descriptives box and look at the standard deviations. This is a 0 to 10 score on a test. And they're all pretty close. 0.3 apart is the biggest difference, or it's less than that, really. And so I would say, ignoring this part, that's the total. So you don't want to look at this line at all. That's pretty close. So yes, so always think about the scale of the variables. So yes, it's okay. Okay, so what now? Well, step 2 is to list your researching your null hypothesis. So we're going to list all the groups. So it's constant sound versus random sound, random versus none. And then the same thing here, constant, random, none. And remember that the DV is my score on the multiple choice test. Okay, so it's not compared to the Ivy levels here. So ANOVA is always not equal to and equal to because of the way that it is calculated. So we're going to say that the groups are not equal. Something is different somewhere. And the groups are equal. Nothing is different. Okay. So we hope that something is different, but it may not work out that way. For step 3, you want to include the descriptives box. That's this bad boy. So we're really looking for the means. We're going to use those in a little bit for our post hoc test. And the ANOVA box. So this is the source table. So this thing we're going to use for R squared. This degrees of freedom thing we're going to use for step 4 here in 2 seconds. And this F we're going to use for step 5. So there's a lot of good stuff going on in this table. So you need that table too. Okay. The next thing you want to do is come up with your cutoff score. Okay. All right, so for our cutoff score, we need our degrees of freedom between. That's groups minus 1. And that's 2. That's here. And our degrees of freedom within, which is n minus 1 plus n minus 1 plus n minus 1. And that's 21 in this example, so here, not 23. Ignore that, right? So we're going to do 2 and 21. Remembering that on these tables, between goes across here. So this is where you're doing groups minus 1. So we got 2. And then within goes down. So that's your n minus 1 plus n minus 1. Go back. Minus 1. There we go. So that's 21. And we're going to use 0.05, I think. If I didn't say, that's what I'm going to go with right now. And so it's this score, but I covered it up. So let's try again. There we go. So it's 3.47. Remember, these are always positive. So it's not plus and minus, it's just 3.47. And to hit that point home, I'm going to draw F here on step 6. Okay, so there are no negatives. This is approximately 1 here at the highest point. That's 3.47. Everything over here is reject the null. Everything over here is fail to reject the null. Okay. For step 5, I have to list F. Remember, F is the ratio of mean squared between over mean squared within. So that 14, so is that found, comes from 3238 over 2.23. So I got 1450. Remember, F can get very large very fast. So having a score of 200 is not unusual. So 14 is not unusual either. So we're going to be way out here. So 14, what did I just say? 50. So as my decision for this step, I'm going to reject the null because we are way past our cutoff score. So our little car on the race has crossed the finish line. The next thing to try is effect size. So R squared is sum of squares between over sum of squares total. So don't use mean square. I have to back up to get to that. So it's going to be here 6475 over 11163. So let's do 6475 over 11163. Yeah. Pull out my phone calculator here. And we've got 6475 divided by 0.63. Equals 58%. Okay, so this is a super huge effect size, remembering that 14 is large. Okay, so 58% of the variance in our DV is accounted for by our IV. Remembering that this is the difference of the IV due to groups. Or not even the IV, it's the variance due to groups. Okay, so it's how much of the variance is due to the grouping variable, or the IV, or the differences between means, over how much variance is there is total. For a post hoc test, I'm going to use Tukey, but this same set of steps applies for Bonferroni. You're just going to have a different box. So if you run this, you will get slightly different numbers than me. And what we're really going to do is use this column. And let me write out all of my comparisons first and then come back to this box. Okay. So I'm going to do group 1 versus group 2. And I'm going to list their sig value, which remember is found P. I'm going to back up. I'm going to hit my compare value. So what am I comparing to? And then I'm going to tell if I reject or not. Reject. Not enough room. Gosh. Right. So to compare this, I've got constant sounds. So I'm going to do everybody versus everybody else. So a constant sound versus a random sound. So that's pairwise, meaning each one paired with every other one. So this is Noah's Ark 2 by 2. And then I'm going to do constant. I'm going to give myself some more room, actually. Oh, no. Okay. There we go. I'm going to do constant. Well, I was trying to give myself more room, and it wouldn't erase. So let's try. Here we go. Pretend that C isn't there. Constant versus no noise. And then the only other comparison there is random versus none. So I have compared every one to every other one. So when you have 3 groups, that means there are 3 comparisons. When you have 4 groups, there are 6 comparisons. Okay. And so I'm going to add the means to these. So what is the mean for constant? And random and none. So let's back up a couple slides here to the descriptives box. More than a couple. Half the slides. Wait, one more. There we go. So the constant group is scoring 6.63. And then we've got 375 and 275. So let's add those here. One more. Equals 6.63, 6.63, 375, 275, 375, 275. Okay, that's going to help me in a minute to determine what happened in the study. Okay. Now I'm going to use SIG. So back up one slide to the post hoc test. So I'm going to do constant to random here. Here's the first significance value, so 0.003. Slides are possessed. All right, that means here, random versus constant. I've already covered that one, so I'm going to scratch that out. So it doesn't matter what the order is that you do them in, and you don't want to do them twice. So SPSS assumes that you are an idiot and does everything for you twice. And then I want to do constant versus none. So constant and none here is 0.000. And you don't want to list anything as 0.000. I'm sorry, this thing's kind of having a fit. So we're going to list this as 0.001 because that means it's just less than 0.001. So anytime you see 000, I sometimes call this the new kids on the block rule, 000, you want to list that as 001. Last but not least, random versus none. And so I've done constant versus none. So I can scratch that one out. So random versus none here is 0.39, and that makes this one useless too. Okay, so you want to use the first two and then this one. All the other ones are repeats. So 0.39 is our last one. See if you can do this without it being upset with us. Okay. So remember, the point of this post hoc test is control for type 1 error. And it does that by changing the sig values for you. So it sort of recalculates the probability of these effects, so the p-value, on its own in the background. And so you don't have to, especially if you're doing Bonferroni, compare it to any specific value, except the one you started with. So if you said p less than 0.05 for step 5, that's what we're going to use here. So less than 0.05. Okay. So it auto does the fixing of alpha for you. Okay, and that's nice because it lets you compare it to an alpha, a consistent alpha, 0.05 the whole time. So, is 0.003 less than 0.05? Yes, so I'm going to reject. Is 0.001 less than 0.05? Yes, reject. Is 0.39 less than 0.05? Nope, do not reject. Okay. So what do I do with this yes, yes, no? Okay, well, it's not super helpful. If I told my mom the results were yes, yes, no, she would kind of laugh and then wait for me to tell her the rest. So that's when you go back to the means here. So the constant noise group has a higher score than our random noise group. That means they are remembering more things on this multiple choice test. The constant store group also has a higher, constant noise group has a higher score than our none group. So they're remembering more items in the none condition as well, and that's no sound. However, random versus none is not significantly different, so they're equal. So I would say that it appears that the constant noise gives you a higher score than random noise or no noise. And random noise and no noise are not significantly different from each other. So it's about having the same, studying in those two conditions will give you the same score. So maybe a constant background noise is good for you. So remember, when you're trying to explain what happened in a study, think about how you'd explain it to your mom, your friend that is anti-math, and so you just kind of try to tell people what's the bottom line. Okay. So those are the 6 steps of hypothesis testing, including post hocs and effect sizes for one way between subjects and ANOVAs.